A very good morning, good afternoon, good evening to all the students, participants and my friends for this NPTEL MOOC course, the title of which is Application of Forecasting Regression and Time Series Analysis and Time Series Models, and my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you know, there are three broad areas: forecasting, second one is linear regression or regression, and third one is time series. And we are in the second part, which is linear regression or regression models. This is week 6 and this is lecture number 26. So, the coverage, if you remember, it was more of an introduction, it will still continue. And if you remember, I did mention what was the plan of coverage for the 25th one, but there were a lot of discussion going on about assumptions, linearity, rank, dependence, non-dependence, what does the matrix imply. So, this explanation with the diagrams were not possible. Hopefully, I will be able to do this in this class. So, continuing with the assumptions. So, exogeneity of the independent variables is another one. The expected value of the distribution, now this is important, at any observation in the sample is not a function of the independent variables observed at any other observations, including this one, which means they are basically being observed or taking the observation from an IID, which is independently and identically distributed distribution based on which we are taking. That means, consider there is a box where there are infinite observations and you are picking up one. So, and there the distribution remains same, maybe it is normal, maybe it is exponential. I am giving an example, maybe it is gamma distribution, maybe it is Poisson distribution, and there is an expected value, there is a variance. So, picking up one observation does not affect the next one, and whatever you picked up in the initial stage does not affect the observation which you are taking. That means, I am picking up from an infinite set of observation, the distribution remains the same. Thus, the independent variables will not carry useful information for prediction of the error term, and that means, whatever the information the random variable x has, it will be pertaining to its effect on y. Whatever the randomness, whatever the white noise, whatever the error is there is outside, and error would not be, technically error would not be affecting the reading of x, neither the x value reading would be affecting the error. That means, they are all so called independent of each other. The assumption of homoscedasticity and non-autocorrelation means each disturbances, now I am going to the realm of errors, each disturbances or errors has the same finite variance, whatever the variance is, and they are uncorrelated with every other disturbances error, in the sense that distribution would have an there is an error distribution, in the sense it has got the expected value and variance, and error of, see for example, the 7th reading would not have any effect on the error of the 8th reading, or it would not have an effect on the 10th reading. If that becomes, there is a problem which we will see later on in time series. So, basically they would be uncorrelated in this case, and of course, this assumption limits the generality of the model, and we want to examine how to relax it later, not in the realm of a regression, but in the realm of time series. So, the concept of non-autocorrelation, if you remember, we have done the autocorrelation, that means how it is correlated with itself in the example of forecasting, if you remember. So, I want to find out the autocorrelation, autocovariance of itself between the yth to the yt minus 1th term. So, this concept of non-autocorrelation will be true, because there is no such correlation existing between the data points. And what is the concept of homoscedasticity? We will come to that in more details as we proceed with the examples. So, the concept of homoscedasticity, heteroscedasticity, all these things would become clear as we proceed. The next assumption is the data which you are using may be any mixture of constant and random variables which you are using. Why a constant? You will see it very soon. The crucial assumption for present purposes are the strict mean independence assumption, which is number 3, and the implicit variance independence assumption in assumption 4. So, 4 and 3, 4 was just the previous one, where the concept of non-autocorrelation concept was discussed, that means they are not dependent, correlation is 0. Autocorrelation being there, which means correlation would be non-zero, and the concept of homoscedasticity and heteroscedasticity will be explained later on, as I said, in due course of time. Also, assumption 3 basically we considered that any one reading for x which I am taking, it would not affect the other reading of x when I am taking. That means I am taking from a infinite distribution for that x, whether it is x1, x2, x3, that is immaterial, because we know, also we are aware that the random variables x1, x2, x3, all the x's are independent of each other based on the concept of rank, which you have already discussed. So, analysis will be done conditionally on the observed independent variables, what we are observing, based on that we will pass on the judgment. So, whether the elements in the independent variables are fixed, constant, or random variables or random draws done from a stochastic process will not influence the test, because the reading based on which we will proceed would basically be assume that x's do have a effect, but that randomness is only limited to that x. And if I am considering the effect of x2 and not x1, then the effect on x1 and x2 would not be there. That means they are always independent of each other. The other assumption which we will consider for our problems, but it can be relaxed also. The disturbances which we will consider, the white noise we consider, are technically considered as normally distributed with a mean of value 0 and a variance of sigma square. Now, here I would like to point out few things. Generally, for simplicity, we may take the variability here as not sigma square, it can be as 1. That means, it will be, in that case the error terms will have a normal distribution with 0 mean and 1 standard deviation, which means is a standard normal deviate. Now, this fact had already been mentioned in regression model. If you remember, in many of the problems I was trying to draw the error plot, and I mentioned in one of the example in detail with one of the time series, if you remember, that was only specific to the time series of a financial data, even though that would become, if I do the analysis in depth, then the concept of time series concept has to be used, but it was clear from the diagram perspective that the average value of the error was almost coming out to be 0. So, this is the fact which is being highlighted in this slide, that the expected value of the error is 0. And number 2, the variance is either sigma square or 1, but what is important to note that the variance is not changing, it is fixed. So, the concept of homoscedasticity, heteroscedasticity would be coming up later on with respect to the variance of the errors. Now, another thing, if the variability is variability means the errors variance are dependent, then obviously we will be going to the realm of time series analysis, which I have been repeating time and again. We will consider that as we proceed. Now, here is the diagram which I said that I will try and explaining here, and this is the 2D diagram, hence it will be easy for us to explain. For a 3D diagram, I will try to plot it here, and for the explanation of all the participants. So, consider I will use initially the x axis which is marked here, along the x axis the variables, random variables x, and consider there is only one random variable x which is being utilized to regress and find out the value of y, which is simple linear regression. So, all the x values are plotted along with the y values. So, here are the values, if you see, I will just use the black color to mark it. So, this value is dot UC is basically x1, y1. For x values of x1, what is the value of y1? Here this is the value of x2, y2. That means, for the value of x, it is x2, the value of y comes out to be y2. Similarly, if you see, I am not going to mark it, I do not want to make it cluttered. You have x3, y3, you have x4, y4, you have x5, y5, and so on and so forth. Now, what is important is that if you see the slanted straight line, That is basically the regression line. We will find out how we calculate it. That is the regression line, and this is linear in nature, because if you remember, one of the assumptions between x and y was the linearity. This is linear in nature, and what is important to note is this. I will use the black color to denote. Let me use the violet color, because the color has not. So, if I find out the difference, the vertical difference along the y axis, the difference between that point and the straight line. So, if I concentrate on x2 y2 with respect to the straight line, this error is E2, because E2 being for the point, the second point for x2 and y2. So, x2 and y2 I am trying to find out is distance from the central line, which is the linear line. Similarly, if I find out the point difference between the point x4 y4 from the straight line, this is denoted by E4, which is marked in dark blue. Similarly, if I want to find out the point difference between x4, x5 and y5, I have the point as E5, which is marked. Now, if you see, the points error have been marked with the suffix E with the letter E, and the coloring scheme has been given as blue and red. Now, why is that? For more clarity, if it is negative error, that means the straight line is above that point x1 y1 or x2 y2 or x3 y3, then it is negative, like as shown in E2. Or say, for example, if you find out for E1 where the distance is very small, but I marked in E, if you basically see the slides, you will understand. But if I see the error term between the points x4 y4 with respect to the straight line, or x5 y5 with respect to the straight line, then that error is positive. That is why it has been marked in color blue. Now, one thing to remember, which I mentioned as I was talking, the distance is the vertical line parallel to y axis. You are not going to basically drop perpendiculars from that point onto the line, or else finding out the error would be wrong. So, the errors which are marked here, the vertical lines are the errors. That is point 1. And if you remember, when I was mentioning the regression model, I mentioned that the main idea was basically to minimize the error. Now, the immediate question which may come up is, how do I minimize the error? Is it that I only add up the errors and minimize it? Which means that I may be able to find out the mean error only. Mean error in that case would be the sum of all the errors, considering there are n number of points 1, 1 to n. Another case can be, I will use a different color, say for example red. It can be mean absolute error. In that case, I will find out the sum for I is equal to 1 to n for all the errors, where I have basically the mod of the errors. Now, the problem for the first part, mean error, which is much more intuitive to understand, it may be possible that the errors are both positive and negative. They are huge errors, but they add up to 0, because there are positive errors and negative errors, such that in the long run they add up to 0. So, you may be tempted to say that the line is very good fit, because your overall sum of the errors is 0, but that may be wrong. So, in order to basically compensate that, if you remember, we have taken in forecasting concept model the idea of trying to find out the sum of the squares of the errors, which means what we do is, I use a different color, consider green. So, for the sum of the square of the errors, I take I is equal to 1 to n. Obviously, because n is the number of reading, I take this. That means, I take the error of the square and sum it up. Now, this has one great advantage. When I try to find out the square of the errors, it gives me direct connotation of the idea of variance. And if we concentrate on the error, and if your main task is to basically minimize the error, which is shown in green colored here, which is square of the error, that means that trying to reduce the variability is one of the best method how you can find out the errors. And why we need to find out the minimum of the errors, we will come to that very soon, because all the study which we are doing, all the regression models we are going to understand would have an implication that what is needed to be found out. Now, on the flip side of trying to find out this minimizing the square of the errors is if there are outliers like very high positive error or very high negative error in the negative sense, then squaring them up obviously, and if you keep adding them, then it may blow up. So, outliers may be possible to basically ruin your or diminish your chance of trying to find out the best fit. But that is not a problem, because when you do a visual check, these errors which are outliers can be found out very easily. So, even though when you are doing the problems, I will highlight that, but when you are trying to solve the problems, we will assume that the outliers are not there and straightforward use the formulas to solve the problems accordingly. The second point is that if you remember, I mentioned about the errors. So, I will utilize the same diagram, erase whatever I have written and plot the error distribution. I will just erase it because I do not want that to be cluttered. So, the explanation for the distribution the errors would be much easier for all of us to understand. Now, here I start to plot the distribution errors, and I will use the green color here. Yes. So, when I consider the error, technically it means that if I plot the error, so obviously the mean value is the straight line, but when I take any random variable, there is obviously fluctuation over the mean, below the mean, and if I consider the normal distribution of that error, I am only plotting first the distribution of the value of y, then plot the distribution of error terms. So, those are two different things. So, if I plot the value of y, technically it will be a normal distribution with the mean value being along the straight line, which is the best fit, and the dispersion will be given by the corresponding dispersion which we are utilizing to find out the value of y. Now, you may be thinking that why am I mentioning about the dispersion of y? Because later on we will see, and this assumption which would be making much better sense, that we have considered the errors as normally distributed with 0 mean and either 1 as standard deviation or variance or sigma square as the variance. In the similar way, again I am mentioning, even though it may not make much sense now, but it will be the statement will be repeated by me time and again. So, let me start using that concept. All the random variables x1 to xk, k is the number of random variables which you have, each would be normally distributed. Obviously, we know they are independent. So, if they are normally distributed, they will have a mean and a variance. So, when you are trying to find out the concept of y, y is dependent on all the x's and it is also being affected by the errors. So, you have basically different normal distribution of x's plus the normal distribution of the error term affecting the value of y. Hence, y will also be a normal distribution as shown in this graph now in the green curve with a certain mean value and a certain variance. Now, the question you may ask that given the expected value or the mean value of x, given the expected value of the mean value of error which is 0, also given the variance of x as well as given the variance of the error, are we able to find out the mean value and the variance of y? The answer is yes, we will be able to find out. So, that is why the line which have been fitted is actually basically the best fit line which gives us the mean value of y as such at that point. So, obviously, at that point the mean value of y is this. So, obviously, the overall dispersion which you have in this region, which I will mark here, is basically the variability of y which will be coming from the variability of x plus the variability of error. And here if you see the variability of x, there is only one x. So, obviously, we will have one variability plus the variability of error which is sigma square or 1 as the case is, and you will be utilizing that concept to find out the variability of y. Now, remember that I am using different concepts. So, if you go through the slides and listen to this lecture carefully, you will understand. If you remember, a point has been mentioned and which I am repeating time and again, independence. So, the concept of independence between x, concept of independence between the error and x would basically have a huge implication when we try to understand the variability of y as well as the mean value of y given these two concepts. Now, if I am able to draw the error distribution, which I have not drawn till now, the error distribution where I am using the y axis as the error reading and the x axis as the reading number. So, if I basically plot the distribution of error, so the error would basically and if it is there are many readings, so the error would be basically fluctuating like this. Is exactly the same way as we have seen in forecasting, and this is the horizontal line has a value of 0, which means that if I plot the error distribution, the error distribution would look like this, which means with a mean value of 0 and a standard deviation of 1 or sigma square, which remains fixed. Another point, if you remember, if I mentioned homoscedasticity, heteroscedasticity, the concept of the heteroscedasticity concept or the homoscedasticity concept would basically imply the errors are independent or independent. If they are dependent, then the future values of the error as I go down the time frame, that the error would basically be exploding with respect to the variance. That is the concept which we will try to utilize in the area of or the domain of time series analysis. Now, here is another graph which is theoretical one, but it will make you help you understand all the things. So, if I consider again 2 dimension one, along this x axis you have the x values, there is only one x, and this diagram just for simplicity I have taken from an econometric analysis book by W. H. Green, which is a classical book. There are fantastic books in regression model. Those who are interested can utilize that, read that. There is Draper and Smith. The syllabus would have been discussed with you. There is Montgomery and all these things are there. But I thought because the name was written here W. H. Green, I thought I will basically mention that. Now, if I see you have x along the x axis, y along the y axis, and this line which is there, which is shown in black bold one, which I am again marking, is the best fit line. And if I take the value at any value of like this, so that would be given by the average value of x and the average value of y. What is the average value of x and average value of y? Because if we remember, if we have n number of y values, n number of x values, then the average value of y would be given. I will use the red color. So, there are n number of readings, the average value of y would be y1, I is equal to 1 to n, sum it up and divide by n. Similarly, if I find out the average value of x, I will use the green color, it will be 1 by n, summation of xi, I is equal to 1 to n. And why I have written that in different colors and explained that? Because we will be utilizing that for our calculation. So, the average value of y, average value of x is written, and they are denoted as x bar, and for y it is denoted by y bar. Bar is the average. And if I consider the values, the x1, y1 values as they occur is given here. One random variable is this point xi and yi. Now, what I have is ei, if you remember, was the error. So, if I basically drop the vertical along the x axis parallel, this is the error which we had and I am marked. Again, I am marking using the orange color. This is the error. Remember, it is not this, it is not this error. It is basically the vertical one. This brown line is incorrect. So, I will erase this because I do not want any confusion. And if I find out the values of, say for example, I am trying to basically find out the values of y utilizing the x. So, the actual value of y based on the regression line is this point which I have, which means there are two things. One is the error which I have already marked. One is basically the difference between y hat. This hat is basically the estimated value or the found out value for the ith reading. So, obviously, as the reading changes, the yth value will change. So, you would also have, these will be required later on for the calculations. You would also have a difference between the y hat ith reading and the average value. Average value is fixed, remember, as I changes, y hat I also changes. And also corresponding to the value, you will basically have the actually the y value, yi actual value which you have, this one, and you will basically have the total amount of difference between, one is between y hat with the suffix I minus y bar, and another is basically the difference between the actual value and the forecasted value. This is what we denote by error. Error, remember, is not the difference between yi and its average value. It is basically the difference between yi and the predicted value, which is yi minus y hat. Now, in the case of forecasting, this y hat was denoted by f. Here we are using a different symbol, but the concept remains the same. So, I will pause here for 2 minutes, have a look at this diagram, understand the explanation, because these values, when you solve the numeric values, would make sense. Another thing before I move on further, and I will erase all the marking which I have done. Now, till now I have been utilizing the 2-dimensional one, which is good, and I also did mention that pictorial I will try to illustrate how the 3D looks like. So, let me try my level best here. So, consider you have the values as x1 along the direction as you see on the screen on the board. Consider x2 is coming out from the screen. So, basically it's the 3-dimensional figure I am trying to denote. So, consider here, I will try to use my hands in order to denote. So, consider the hand which is here is basically the x1. Consider for your case, even though it's given that's coming out of the screen, consider the one which is going towards you is basically x2, and consider the y value is being mentioned in the vertical direction. So, again I will mention the horizontal, my right hand which you see is x1, my left hand which is going towards you is basically x2, and they are orthogonal and perpendicular. So, if you look from above is a 2-dimensional, like basically a sheet of paper, and the y axis which you see is basically vertically up. Also remember, y to x1 is 90 degrees, y to x2 is also 90 degrees. Now, what we have is basically a 3-dimension like a room. Now, all the readings for x1 are being measured along my right hand, all the values of x2 are all being measured along my left hand which is going towards you, and all the readings for y are being measured along the vertical direction. So, if you see the vertical line which is the best fit, if you basically imagine that being done for this 3-dimension, then in that case the best fit line on the regression line would now be a plane, not a line, a plane, and any other point which is there in the space which is denoted by x1, x2 and y1, x1, so it's x11, x21 and y1. So, then the second suffix 1 is basically the first reading. So, that would basically be a distance which is drawn vertically parallel to with respect to the y axis onto that plane. So, that would be the error. So, if I have x1, x2 here and the plane is like this, and the point x11, x21 and y1 is here, it will be the vertical drop which is there, that is the error. Similarly, if I have the second point as x12, x22 and y2, and again this is the plane, if the point is here, is the vertical drop which is there, which will be given by the error marked as 2. So, in the same case I will try to basically find out the squares of the errors, sum them up and try to minimize that. And when you are trying to minimize that, that is basically the essence of regression which I have been discussing. So, the line, the diagram, and similarly, sorry for that, similarly the plane which you have, at one point you will basically have the average of x1 bar, average of x2 which will be given by x2 bar, average of y which will be given by y bar. And similarly, you can utilize the concept to find out the error, the difference between y hat I and y bar, then find out the values of the difference of yi minus y bar hat I, and correspondingly another value which I missed, which I should mention, but it would have been coming up in the discussion later on. You find another term which is given by this b into xi minus x bar is basically that b component has an implication which is basically a slope of a curve. And what is the slope of a curve? I will come to that within 2 minutes. Please give me few minutes more. So, when I am trying to find out the regression line, if you remember, this line would remind you of your class 10 and 12 basic trigonometry, where you had that line as y is equal to mx plus c. And here the value of m is basically the slope, which means that the rate of change of y as x changes by 1 unit. B would have that implication, which is the rate of change of y with respect to x. And that point C which you have is basically the intercept, and I will make it you understand as you proceed. So, in case if you have basically the 3-dimensional one, again I am making the gesture with my hands. So, you have basically x1, x2 and y, then in that case obviously you would have an implication of the rate of change of y with respect to x1 when x2 is kept constant, and that is important. I will come to that later. Similarly, you will have the rate of change of y with respect to x2 when x1 is kept constant. So, that concept of rate of change or the so called the factors of, here it is given as b. So, for the 3-dimension case it will be b1, b2, b3, considering the dimension is increasing. They will be discussed in more details with diagrams. So, with this I will end this class and continue further discussion of the assumptions along with the problems as we proceed. Thank you very much and have a nice day.